Okay, so thank you. Okay, so let's go back to normal force. You have to think that any surface that you touch, okay, maybe you sit on a chair or you push on the wall, will behave like a giant spring scale. So that type of spring scale. So whatever is going to feel on it is going to push back. Now, it doesn't mean someone said, oh, the object has to be at rest. It's not necessarily true. It doesn't mean that the thing is not moving. I'm going to tell you why. But again, this example here, imagine the desk here is a giant spring scale. So it's feeling the push, right? So you have the weight here because Earth is grabbing the block, pulling it down. So you have 15 Newton down from the weight, but you're also pushing down. So the bathroom scale, imagine it's a bathroom scale, it's going to feel 26 Newton. So it's going to push back with 26 Newton. So in that case, the normal force is going to be 26 Newton in magnitude. So the normal force is a reaction force. It's reacting, right? So you can imagine here, inside those devices, you have like a spring. And as you squeeze the spring, it's going to push back, right? So in this case here, it doesn't feel the 50 Newton down because at the same time it's being the block is lifted. Okay, so it doesn't feel the same push. It's gonna feel 15 minus 11, so it's gonna feel 4 Newton down, so it's gonna push back with 4 Newton up. Is that clear? So that's the normal force. There is a different way to do it. Okay, in equilibrium, you can say everything up has to be equals to everything down. What is up? 11 plus IDK equals 15. So IDK has to be 4. This is in equilibrium. It's called static equilibrium because it's at rest. So everything up has to be equals to everything down. What is up? IDK. What is down? 11 plus 15, 26. So up has to be 26. Okay, this is also, as we discussed, if you join the Zoom, right? It's also called the apparent weight. Okay, that means if you put a bathroom scale here, you're gonna read 26 Newton and not 15 Newton. Okay, and if and I will get back to that. But if you take the example of someone accelerating up in an elevator. So if you take this case here, but I will get back in the next unit. So just to show you that it does not have to be at rest. Oh, because this is okay. Let's say if it's upward acceleration. So someone here is inside an elevator. So this is the person here. Of course, the elevator has to accelerate to reach a cruising speed. So you go from 0 to a given speed. So the floor here has to push you up. Does it make sense? Because you want to stay where you were here at rest. You have inertia. So the floor is pushing you up. Okay? Because it's accelerating. So you're going to feel what? Heavier or lighter? Heavier. Very good. Now, in physics, we're going to define a system. So if I define the system like being the guy, just the guy, right? That's my system. What are the forces acting on him? So first of all, let's not forget Mother Earth, right? What Mother Earth is doing? Pulling him down. So pulling down. Oh, I'm not doing. So pulling down. And pulling down with a 700 Newton because that's his real weight. Okay, but then what is the other force? Normal force. Now, be careful with that. It's all about the net force. Do you think the normal force will be equal to 700? No, because in that case, the net force will be 0. If the net force is 0, it's either at rest or at a constant speed. That's not true because there is an acceleration. So the normal force has to be larger than your weight. Okay, so in that case, it will be 1000 Newton because it needs to accelerate the person in the elevator. Does it make sense? So it's all about the net force. Remember, if the net force is 0, so what is the acceleration in that case? 0. Net force is 0 means equilibrium. Means either you are at rest or you are moving at a constant speed in the same direction. If the net force is not 0, so first you need to find the net force, you add vectors. That's why I was very annoying, insisting that you understand how to add vectors. So the net force is not 0. That means you do have an acceleration. So the acceleration is just the net force divided by the mass. Remember, from the beginning I told you acceleration is in the same direction as the net force. Is that clear? So what is the net force in that case? You have 1000 up, 700 down. 300 which way? Up. Okay, so what I'm gonna make a free body diagram because physicists do not know how to draw. So we take a XY coordinate system. We take this guy here in a bag, shrink it to a dot. Okay, you make it as a dot. I'm gonna say, okay, so you have 1000 up and then 700 down. Okay, so what's going to be the net force? It's going to be, so you can make another free body diagram. Everything happens like this guy is only acted upon by 300 up. When I want to find his acceleration, all I have to do, but that will be for next time, F equals ma. You divide the net force by the mass, and I will know the acceleration. That's why, remember I told you, always find the net force. Once you have the net force, you know which way is the acceleration, and you know the magnitude of the acceleration. Okay? Yes. Yeah, the acceleration of the elevator will be the acceleration of the guy. You understand? So if you take that's a good question because it brings me to another question here. Now, if my system, I don't care about the guy. I'm just want to focus on the elevator. How does an elevator work? What are the forces acting on an elevator? How come it's going up? Tension, very good. The tension, right? So the tension has to be very large here. And of course, you have the weight. What's going to be the weight? It's going to be the weight of the cage and the weight of the guy, right? And it will be the same acceleration. So it all depends on which system you are focusing on. So it's like you take a bag and you put whatever in your bag. Is that clear? Tell me your name when you participate, right? So for example, here you have an inclined plane, okay? So first of all, I want you to memorize. If you have issues with inclined plane, because I've seen those for the MCAT, for example, it's very easy to trick students. So if you have an inclined plane, So you see the x-axis is always along the plane, and then here you have the y-axis. When they ask you, like if you are asked to find, to make the free body diagram, the weight is always straight down, always straight down, always straight down. The normal force is always perpendicular. Perpendicular to what? Perpendicular to the snow in that case. Now you see, a vector comes in two components. Each component has different consequences. So here you have the x component of the weight, and here you have the y component. Okay, remember, the tail is at the origin, and the head, that's where your components, that will be the components here. Okay, and you can memorize the following. If you have 60 degrees here, that's going to be 60 there. Okay, you can convince yourself using simple geometry, or you can see me at the end, but 60 here, 60 there. And you can memorize the following. The y component is always mg cosine. So in that case, it's going to be 60. And the x component is always mg sine. So if you do a little bit of geometry, you can see. Otherwise, you can memorize. Now the acceleration is along what? The x, the y, or somewhere in between? X. Okay? So this is not in equilibrium here. It's the x component that will provide the acceleration. Do you agree? Now, what's happening along the y? Nothing. The normal force is being balanced out by the y component of the weight. They kill each other out. Nothing is happening along the y. There is no acceleration. The acceleration is just along the x. So if you are standing, so typical question for a pop quiz. If you are standing, so maybe you know there is so much static friction that you manage to stand on the bathroom scale here. The weight that you're going to read, is it going to be your true weight? Is it going to be less, or is it going to be more? Less. Remember, like we can cheat with that because the weight straight down, however, it has two components, and it's only the weight component pushing on the bathroom scale. So the bathroom scale is pushing up, and the x component is busy trying to fight against what? How come it doesn't go down? Friction, very good. What type of friction? Static friction. See, the zoom worked well. Static friction, right? So this is called static equilibrium. It's not going anywhere. All the forces are killing each other, which means up equals down, left equals right. In this case, there is no equilibrium because there is an acceleration in this direction. Is that clear? Now, if I decide to add the forces, so if I take this force plus this force, okay, I cut and paste, tail to head, what do I get? I'm gonna get this one. That will be your net force, okay? That will be the net force. Because this one is being murdering this one. They are killing each other out. Okay, so it doesn't count. So this one plus that one, you add the forces, you get the net force. Is that clear? Yes. Okay. So you cannot say that the normal force trying uh, to break the object at rest is not necessarily true because of the elevator. Right? So in that case, you see it's accelerating up, but it's not at rest. Okay, so we did all that. So if you missed the Zoom, I hope that you all catch up. Okay, okay, we're gonna do, did we do this one? Okay, let's do this one. So you have two ways to do it. You can find the components, you can show the components right? And you say everything up equals everything down, everything to the right equals everything to the left, or you use the long way. Okay, so the goal here is like it's a force table, and don't wait for me. Or it's a force table like something like this, right? Exactly that. Okay, ring, the ring does not move, so it means it's equilibrium. You have one force here, so T1 is the tension, T2 here, it's another tension, T3 is another tension. When you're gonna add the vectors, tail to head is coming back to the same place, so they are killing each other out. Or you can also say that the sum of the components will be zero. X component will be zero, Y component equals zero. So the goal here is to find, like we did last time, if you do not miss the zoom, we need to find the third force here. So the thing doesn't move. Yes, so you see, if you didn't miss the zoom, it's much easier. You didn't have to catch up. So this is the ring here, and you want to find F sub 3. And you don't stare, you do it. You have two ways to do it. So what does it say? It says this is 10 Newton here, this is 10 Newton here. Okay, so this is 30 degrees, and this is 30 degrees. So first thing, you're gonna bring all the information that is given to you on that diagram. And obviously, if you didn't miss the zoom, you know that's gonna be the other force here will be here, right? Gonna be here. Okay, so next, you always want to show the components. So let's say I'm gonna call that T1. I'm gonna call that T because it's tension. So T1, that's gonna be T2. So first you make the components, right? So there's gonna be X component here, Y component is gonna be up, right? T1Y, and then T2 X and T2Y. So nothing new under the sun. We have done that a lot. So Y component is pulling in this direction, Y component is pulling in this direction. They have the same magnitude because this is the same angle, and you need a force here to balance out, right? Okay, so you have two ways to do it. You have the long, annoying way, okay? Remember, you have T1 has two components. That component, you see, this is 60. This is 30. So if you are using 60, then you can take the cosine. Cosine 60 times 10, or you can do 10 times sine 30. Now you all know trig or polar graphs or whatever. So what's going to be the x component? Huh? No, the x component of T1. 5. Very good. And the y component? 8.7. Very good. And then T2, you don't have to do trig because you see T2 has exactly the same component as T1 except it's going to be negative. Very good. So negative 5. And the y component will be also exactly the same. So it's going to be very good. Right? So with a drawing, you can have shortcut. And then T3, that's what you want, right? So I'm IDK. T3x, T3y. So, and you know that the sum has to be equals to 0 because it said it's in equilibrium. If there is no acceleration, that means the net force is 0. If the net force is 0, the x component is 0 and the y component is 0. So the net force here will be 0, 0. So what's going to be the x component of T3? 0. Very good. And what's the y component? Yeah, very good. negative 17 Newton. Do you all agree? So that's one way. Easier way, you can say it's in equilibrium. So everything up has to be equal to everything down. Okay, so what is up? So that will be the x component of T1 and the x component of T2. And they are both equal to each other, right? Okay, so a y component is how much of T1, for example, is along the y. So now I say that T1y, okay, plus T2y, which is the same, equals down, which is T3y. So this is 8.7 plus 8.7, but that works only in magnitude, okay? There is no minus here. It's just magnitude. And then you see the magnitude of, so that's the magnitude. That's the vector, so that's going to be 17 Newton. So you get the same thing. Do you agree? Mm-hmm. And then you see you have also everything to the right equals everything to the left. So what is to the right is T1x. What is to the left is T2x. And we already knew that, okay, because that means T1 equals T2. Is that clear? Now you can make things more complicated if instead of having the same angles, you can have a different angle. But then you will have to solve two equations with two unknowns. We shall leave that for algebra. Okay, so for our class, we're gonna stay with the same angles here on both sides or of something with only one equation with one unknown. Okay? Let's see. Well, this one is easy, but let's do it very quickly. I think it's from your homework. So it's the same idea, okay? So you can help each other do it quickly. Okay, so it's a half a box. So let's make a drawing first. Don't wait for me, okay? Do it on your own. So it's a box. So it has two tensions here, T1 and T2. Okay, that's the vertical. And it says this is 40 degrees here and 40 degrees. Oh, this one is a little bit different. And then you have the weight here. And the weight is 400, so it's going to be 4,000 Newton. Okay? So it has, so you can make your x, y axis here. So this is x, this is y, and this is the x component. X component, they are the same. And then you have y component up here and y component up. Okay? Do you agree? Mm-hmm. So this one is a little bit more challenging. So if you say you have different way, both ways will work, right? So you can say everything up equals everything down. Okay? So up, what do you have up? What is pulling up? Tension. The tension, but the y component of the tension, right? So you have, for example, the y component of T1 plus the one component of T2 only in magnitude. Okay, forget about the sign. This is when you use this way, you only do magnitude. And what's down? 4,000. Do you all agree? Now, second thing I know, the tension will be the same. Do you agree? They're going to be equal to each other. So instead, I can write like T2Y, which is easier because we are in the first quadrant. And this is also T2Y equals 4,000. So try to finish. So you combining like terms. One potato plus one potato is two potato. Yeah, I used to teach algebra, so I used to say that. I don't know why potatoes. You can do it with tomatoes too. So this is the y component, okay? Each component has a different job. It's this component here is how much of T2 is along the y. So T2 is not pulling in this direction. Say the component will be smaller because if you take a right angle triangle, this is the x component, this is the y component. So that y component is not the same thing as T2. Agree? So the y component here equals what? 2,000. Do you agree? Okay. Now, if you like to use the first quadrant, remember, if you use the polar graph, for example, starting from the positive x-axis, you go counterclockwise. So that's going to be 60 degrees here. So the y component is always the sign. So what's the magnitude here? We say we don't know. So T2, uh, what? Do you know I'm like old, so I cannot hear what you say. What? Yeah, yes, you're right. Thank you. Who said that? Gabby. Yes, thank you. I was checking if you were paying attention. Gabby is paying attention. Thank you. 50. Oh, who is Ferdinand? Ferdinand. Fer, no, no. You know, during the Zoom, I kept doing the mistake. No, there was a Fernando, no, it was Fernanda. Fernand? Fernanda, sorry. Okay. No, okay. I just wanted to put a face, sorry. You have to be patient, okay? I'm not everything is not working perfectly. So T2, that's gonna be a sine. So sine 50 equals 2,000. Do you agree? Okay, so what's gonna be T2? Two, 200, 610 Newton. Okay, do you agree? So once you understand how to find components of vectors, right? And you're okay with cosine and sine, that's not that hard. Now, is there a different way to do it? Yes, you could have done the other way. You could have done T1, okay, has a x component and a y component and blah blah blah, and you will get the same thing. Okay? Okay, let's do something interesting here. So that comes from your book. Okay, so I'm using the slides from the Johnson and Chutney Physics, which is very good for students in biology or wants to go to medical field. So this technique here, I think it's called traction. So for example, if you break a leg or if something is wrong here, you want to make sure that the bone is aligned. Okay, so it does not fix. I mean, you want to make sure that it's going to be fixed the right way. So you want to pull on the leg, right? So it's pulling on the leg. But remember, it's all about the system. So you have a pulley here, right? So what's going to happen? The pulley is pulling on the leg, right? So the leg is going to pull back. So that will be the force in magnitude. That will be the force that is pulling on the leg. You can feel that, right? You can see that the leg is going to be stretched out. And you see, you don't want to do any mistake because it can make things worse, and you don't want to have a lawsuit as a result of that. So you want to make sure you do it right. Now, ask your guts. Do you agree? So first of all, when you have a rope like this, right? The rope cannot be stretched out. So do you agree that it will be the same tension being transmitted? So what's going to be the weight down there? Very good, 22 Newton. So you're going to have 22 Newton here and 22 Newton there, right? That's the force on the pulley. That's not the force on the leg. The force on the leg will be exactly in the opposite direction. You know what? When they do that, but they don't use the same technique, it's a horrible. I think it's so horrible, but I don't know. I think in China, some people want to have longer leg. So what they do, they cut the bone. They cut the bone, um, and then they stretch the leg, but a tiny bit. The stretch, constantly stretching on the leg, right? And what will happen is that new bones will be made, and then they start again. So little by little by little by little, they're gonna have a longer bone. But then it creates all kinds of side effects. So I don't know if it's the best idea. Okay, so can you try to solve the problem? The problem is find the magnitude of F. So you can divide the tensions into components. And then you see everything to the right equals everything to the left. Everything up equals everything down. If you don't like that way, you can use this way. You can find the x component of T1, the y component of the y component of T1, the y component of T2, the y component of T2, and the net force has to be equals to 0. So you have two ways to do it. Okay, so help each other. Now we have x-axis here, y-axis there. Yeah, yeah, you can do that in your head. If you do it in your head, you will say 22 cosine 35 times 2. You're right. Yes. And then along the y, you just kill each other out. Okay, so whatever is pulling to the right, indeed, will be the x component of T1 and the x component of T2, and they are both the same. So if you do it in your head, you can do 22 cosine 35 times 2. That's going to be the answer. Okay, so first of all, that's going to be 22 Newton. So the tension is transmitted all over. So that's going to be 22 Newton. That's going to be your y-axis. The tension comes into components. You have the x component, which is busy pulling in this direction. That's the x component, sorry. So you have another x component here, and they're going to be the same because it's the same angle. And you have the y component here and the y component there. T to y, T1x. Okay? And then you can say everything to the right equals everything to the left. What is pulling to the right? It's going to be the x component of T1 plus the x component of T2. What is pulling to the left? That will be your unknown. And you see, they are equal to each other. And what's the x component here? It's easy. It's in the first quadrant. So it's going to be T cosine 35 plus T cosine 35. That's going to be your F. So F equals 22 cosine 35 times 2 in magnitude, because F is pulling to the left. So F will be equals to 1, 1, 36, right? I think I get all, I cannot, who said that? Gabby. Okay. I'm getting old. That's very bad. 36 Newton. Yes. I don't see and I don't hear. So 36 Newton in magnitude. Now, the force is a vector, so we can put a negative. Oh, is that clear? Now, everything up equals everything down. So it doesn't bring us any information. It just says that T1y will be equals to T2y. So T1, and then you have a sine 35 equals T2 sine 35. It just means that T1 equals T2, but we already knew that. Now, if it's hard, okay, if you think it's hard, okay, depends on students, then you can do it this way. You can say T1, T2, and then you have F, and then that will be the long way, and then the net force here equals 0, 0. And then you have T1, the X component will be 22 cosine 35. So I don't know what it is. So it will be half of 36, which is, says this at 18. So it will be 18. And Y component, whatever. T2 will be also 18. And that will be X component. So you see the X component will be negative 36. Okay, and you can, here it will be equal to each other. You copy me? Okay, so F2 sine 35. So this is 12.6. So here we get 12.6. Here we get minus 12.6. And that's F sub y. So you see that F sub y equals 0. That's if you want to take the long way. Otherwise, you take the short way. Is that clear? Equilibrium, everything up equals everything down. Everything to the right equals everything to the left. Let's see. What next? Okay. Oh, there was the one problem in the assignment that is due this week that I found challenging because it should be moved to the next homework. So I changed it, but I gave back, 2 students have done it, so I gave you back the points. So anyway, what do you think here? So we want to, so the main goal here is to draw. So let's focus. So her name is Little Susie. It's a famous drawing by Paul Hewitt. Okay, he's the author of the book Conceptual Physics, and he was very famous. He is very famous for drawing. So this is Little Susie. So what's her mass? What's the mass of Little Susie? 37. Very good. So this is the bag, okay? She's like imaginary bag. So there is the earth grabbing the bag down, and now I don't want to cut her hands here. So what are the other forces acting on her on this system here? So gravity is down. What else?
Tension pulling up.
Pulling up. How many? How many are pulling up? Two. Two. Do you agree? It's two. Those two need to add up to 300, right? So I need to make them half. The size should be half of this 300. So how each one is 150. Very good. Do you agree? So everything up 150 and 150 has to be equals to everything down, which is 300. Okay, so it means when you add the vectors, it has to be equals to 0. If the vectors are not along the vertical, you need to do tail to head or head to tail, whatever. Yeah.
How exactly does the tension get transmitted through the pulley? Does it then at itself separate some of it's on the what's important pulling, some of it's on the right?
So here we suppose the pulley does not have any mass, but the rule is that the tension is transmitted all over. So it means you're gonna have the same tension here. So that's gonna be also 150. But we don't care about what's happening here because we are focusing on only little Susie. So little Susie is being pulled 150, 150. But you're right, that's going to be the same force. So for example, if I go back to tension, it was somewhere here. Tension, the rule is that the force is transmitted along the rope. So at any point, so if you cut that rope here, at that place here, it's going to be the same tension. Yes. So the pulley, we suppose that the pulley has no weight. But so, then it will not be the same system. So you're right. If you look at the pulley, if you focus on the pulley is going to be supported up, right, and it's being pushed down by the rope. So the pulley is also in equilibrium, right? So it will be because here you go from horizontal to vertical. So if you just focus on the pulley, of course, it's going to be pushed down if it has no weight. It's going to be pushed down by the rope, okay, pushing like this, and then it's going to be pulled from the ceiling. So it depends at what you are looking at. If you are looking at the wall here, that support here, you see maybe you have a hook. The hook is going to be pulled by 150 and it's going to be pulled back in the opposite direction. So that's why you need, it's a good question because it's very important to decide what is it that you are looking at. If you are looking at Susie, everything else you can forget. Okay, you can erase all around, and you are just focusing on the forces acting on Susie. So it's a very important principle in physics. You define your system, you put your system in an imaginary bag, and you focus on that bag. Uh, I don't know. Oh, the pulley here is being pushed by 150 Newton on it, pushing it down. Yes, pulling up. So 150 down, 150 up. But we don't care about the pulley. We focus on Susie. Yeah, but you also have here, it's going to be divided between the ceiling and the pulley. Yeah, 150 here, 150 there.
But then you also have another 150 on the wall.
Yeah.
So there's more weight above Susie than on Susie.
Right, so 300 here, here it's going to be 150, and here it's going to be 150.
We follow that 150, it doesn't split itself, it becomes 200.
No, here it's going to be 150, and then it's going to be 150, and here it's going to be 150 all over.
So the pulley's in equilibrium.
The pulley is in equilibrium, but we don't care about its weight. Right? So the pulley is in equilibrium, so it's going to be pulled from the ceiling and it's going to be pushed down. but we are only focusing on this system here. Yes, you just care. And now we're gonna see. It's a good question because it brings there's a paradox like this when you look at uh, I don't know if I can find it. No, this is our class or this is not our class. It's a paradox with the horse. I don't know if I can find it here. You see, if you look something like this, you say, okay, the horse is not going anywhere, right? He's pushing the ground is pushing back, and he's pulling the wagon, and the wagon is pulling back. So how come the horse is moving? However, you need to focus on the system. So if you are only looking at the horse, only two forces are acting on him. The ground, because he pushed the ground pushed back, and the wagon. So then he will move. So you always focus on one system. So let's go back to little Susie. Little Susie. There was not a song like this. Okay, so here in this example, just draw. You want to draw, try to draw it on scale, tension 1 and tension 2. And remember, those two tension, they need to add up to the weight when you do go tail to head. Because they try, because they need, if you don't want to break anything, they need to balance out the weight. Is that clear? And I think you have, I don't know if you can, if I have it here, but you have one assignment like this. I don't know if it's here. Okay, so don't wait for me. I'm looking for it's one assignment. But let's do the drawing first, right? So now we replace Susie by a sphere. It has a weight W. So you want to draw T1 and T2, but you want to make sure it's on scale. So that means T1, you did that for the lab, and T2 are vectors. And when you do tail to head, they need to be equals to the weight in magnitude, right? So try to do that. So you see, you have a weight down, so you need exactly the same thing up, right? So you have a T1 and T2 that they're gonna add up just to provide this force here. Okay? Where should I stop here? You see? See, you make a parallelogram, and you see that's gonna be T1, and that's gonna be T2. If you do tail to head, can you see that when you add T1 on top of T2, you're going to have this vector here. This vector has exactly the same magnitude as this one, but opposite direction. You did that for the lab. Usually you do it for the lab, right? So what can you say? T1 plus T2 plus W equals 0. Agree? Mm-hmm. So let me ask you something. If you have an XY coordinate system, okay, so I have my Y and here I have my X. Do you think T1 has a Y component? No. So which of the two tensions is in charge of supporting the weight? T2. T2. T1 has no Y component, only T2. So T2 has to be very large because its Y component will support the weight and its X component is just busy fighting with T1. So this is the X component here for T2 and this is the Y component for T2. Agree? Mhm. So everything up equals everything down. So what is down? Very good. So down equals up. Everything down equals everything up. What is down? That's going to be the weight. And what is up? No, 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 no. Up, 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 up. Yes, the y component of T2. The y component of T2, right? T1 has no y component. Do you see? So this is why when you have this configuration, so typical for a pop quiz, if you have this configuration, which one will support the most weight? I mean, which tension will be largest? T2. T2. If you touch it, you can do the experiment. Why don't you do the experiment? You can always do experiment for even for extra credit, right? You have something heavy, you have a tension here, maybe leave someone carry it, and then you have a tension there. Just touch it here. The tension, like a guitar. When you play guitar, some string will have more tension. More tension means higher frequency. So here you touch it with your finger. You see this is high tension, and that will be low tension. And this is why. Is that clear? Mhm. Okay, so that's why when you do assignments, you don't want to skim through or look at the solutions to get 100. You really want to understand. That's why I was emphasizing finding component. It's not just to have grade. It's to build up for what's coming next. So that's why. So anyway, so y component is down. The weight is down. Yes. Okay, so you want to kill that weight. So you're gonna have two tension, T1 and T2. So in that case, they're gonna be equal to each other. Um, so we want to have like, that's gonna be T1, and that's gonna be T2 here. And you see, it's the y component. It's only the y component that are doing the job. So the y component of T1 plus the y component of T2 equals the weight. And you can see that by adding the vectors. The x component, they are doing something else. Okay, they just pull on each other. Is that clear? Mhm. Okay, what about pulleys? So pulleys are what we call machine. So machine are to make your job easier, right? So there is something called what is it called? Mechanical advantage. It means how stronger you will get. So if you have a pulley like this, right, how much stronger it makes you? Yes, two. So what's going to be the tension here? So you have 100 here. So again, it's a good question to bring this up because the system here is just your load. So this is called the load. So you have 100 up. How much tension you're going to get in each string? 50. Do you all agree? But follow the rope here. It goes. So what's going to be the tension here? 50. So the load is 100. The load is 100, but you only have to pull 50. So that means the mechanical advantage is 2 because your output, the output is your load over the input, and the input is your effort equals 2. Yeah, there is a price to pay. There is always a price to pay. There is no free lunch, right? That's what they say. There is no free lunch. So for example, if I take one pulley here, okay, so one pulley, it's easy, nothing special, right? Do you agree? It's just changing the direction of the force, the load going up, and you are pulling. Now, if you take two pulley, now you see the load is 490, but your effort is divided by 2. Do you see that? The price, there is always a price to pay. The distance, I have to pull more. So it means if I pull 10 inches, the load will be lifted 5 inches because you're going to have 10 inches here, 5 here, 5 there. So there is a price to pay for conservation of energy. Okay, so if I pull 10 inches, the load will only move by 5 inches. So how do you remember that? Remember when you can lift a car, if you have to change your tire, they have this device, right? You keep pushing, 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 pushing. You don't do one push and the car is lifted. You have to keep pushing and pushing and pushing and pushing and pushing for the car to move a tiny bit. So of course it makes you stronger because you can lift a car, but the price to pay is that you have to apply the force over a large distance. Got that? And so if I have 3 pulleys now, what do you think? Okay, so it will be divided by 3. So it's like you are 3 times stronger, right? And the distance will be less. So if I can do that here. So let's do that. Your effort, that's the load. What's going to be the effort here? 100. 100, very good. So here, again, I have to be careful on the system. And test 2, you always have a pulley because it's cool. So you have 100 here, down. My system will be this. This is what I have in my bag. I don't care about anything else. So it's being touched by 2 strings. One here and one there. So this one is 50 and this one is 50. Do you agree? So if you follow along, this is you here pulling. You're going to pull with 50. It makes you twice as strong. The mechanical advantage is 2. Now, if you have 3, so again, this is your bag, and it's being grabbed by the earth, so 100 Newton. It's being touched by 3 strings, so 1 and 2 and 3. So each string will be 100 divided by 3. So, and if you follow along, so that will be 33 Newton. Agree? So you follow. Now it's going to be 33 Newton because it's the same tension through the rope. Is that clear? And now you have, it becomes a little bit complicated. So 100 here, Newton. And then it's being, that system here in the back, it's being touched by 1, 2, 3, 4. So 4 tensions. So it's going to be 25 Newton. And keep doing this for the load to move a tiny bit. So if you want the load to move let's say 100 inches, you have to pull for 400 inches because that's the price to pay. And here, how many strings do you have? 6. So you have the force will be divided by 6. Okay? So typical question. Okay, coming back to the question, what is the system? The system is the piano. The piano has 1000 Newton down and is being pulled or touched, if you want, by 2 strings only. We don't care about the other things. And each string you're going to have 500. And that 500 will be transmitted. So you're going to pull with 500. That's pulleys. Okay, is that clear? Um, let's look at one assignment which maybe was it has pulleys. So that's one problem. Okay, I remove one problem which was a bit challenging. Make sure to stay on track. If you fall behind, now physics is not hard if you stay on track. Okay, so this one has a big mass and this one has a small mass. And of course, the tension is transmitted. It doesn't have to be transmitted if the pulley has mass, right? Because if pulley has mass, you have to pull harder on one side than the other side. But they say the pulley does not have mass. So first of all, which way it's going to go? Is it going to go counterclockwise or is it going to go clockwise?
Counterclockwise.
Counterclockwise, very good. Okay. So it means you're going to have an acceleration. So that means there is one force which is the winner, right? There is a net force. So let's look, first of all, I'm going to put this one in a bag to see what's going on with this. It has a large mass. So first of all, what is the force pulling down? Gravity, okay? The earth grab, fall. What else is acting on it?
The tension.
The tension up. But that's where I want to be careful because where is the acceleration? Down or up?
Down.
Down. So where is the net force? Down. Very good. In the same direction as the net force, right? And the net force has to be in the same direction as the acceleration. So when I'm going to trace the tension, should it be the same size as W? Should it be smaller or should it be larger?
Smaller.
Smaller. Excellent. Excellent, right? It has to be smaller. This tension has to be smaller than the weight. So that way, when you add them up, you see the net force will be in this direction. Okay, so this is called sometimes, if you want to look smart, you say FDB. Oh, I made a FDB today. Oh, what's a FDB? It's called, it's named, it's a free body. No, you see, I'm dyslexic. FBD. FBD, sorry. Free body diagram. FBD. Okay, so now you know FBD. Oh, that's a good question for a pop quiz. What's a FBD? Okay, what's happening to this one?
It's going up.
Ah, very good. And so which one has to be larger now? So first of all, is it the same tension? You go like this. Yes, it's the same tension because the same force is transmitted. But now which one is the larger?
The tension.
The tension is the largest. It's going to be the same. Okay, right? It's the same. No doubt. But the weight here has to be smaller. Okay, so that's one problem from the assignment. This one has to be larger because now the acceleration is up this way. Do you agree?
Mm-hmm.
And we're going to see sometimes it's you can think of the system if instead you put both of them in a bag. So it's like you have a big bag like this, right? You don't know what's going on inside and you don't care. And the only forces acting now gonna be W1 this way and W2 that way. And inside you have the two masses. And even though you have tension, you don't care what's going on. You don't want to be involved. The interaction. Everything happens like you have a big system here. W1 is pulling here, W2 is pulling there. W1 is winning. Mm. Not sick, okay? I just have allergy. Hmm. Okay, let's see. I'm gonna skip through. So that's a video that I usually do in class, but I have so much things to carry that I didn't bring it. But I last time I took a video. Hi guys, so if I it, so here you have a weight, and the weight is 200. Okay, so what are the forces acting on the weight? You're gonna have the weight and the tension up, right? They are equal to each other. And what you can see is that I skip to 220. Now, if I do it this way, right, there is so much opportunity for extra credit if you put the work in. Now you see that it's going to be 100. So 200 down, 100 here, and you can measure that with a spring scale. Instead of reading 200, I'm going to read half, 100. Okay, you can do it. It should be done anyway. Physics, when it's taught the right way, first you do the lab and then you do the theory. So if you do that for a lab, you see 200 down, 100 here, 100 there. Okay? Do you agree? And I'm gonna skip again. It's in my, by the way, it's my playlist. What do you think you're gonna read here? Be careful, it's a tricky question. So 200 is the weight. So how much here? How much there? 100 and 100. So what is it I'm gonna read? 100. So the only thing that you are doing, it's more convenient to pull down than it is to pull up, right? So it's just more convenient. But the force will be the same, 100 and then 100. Okay? Six. So why is it so important? Okay, if you go to exercise science, it's all about machines and it's all about equilibrium and it's all about injuring, like people injuring themselves. Okay, so here now I have an angle. Is it going to be 100 or on 100 or is it going to be more? It's going to be more. You see, you can even touch, it's going to be more. Because now the tension will have two components. One component will lift the weight, so each component can be 100, but it also has X component. So the hypotenuse has to be more than 200. You see that? Now if you can make a draw, you see 200 here. The y component has to be 100. The other y component has to be 100, right? But you have also x component. So this tension here has to be larger than 100. If it's 120 degrees, it will be 200, by the way. Is that clear? Mhm. And do I have another one? Oh, and if you pull on the side, this one will be less than that one. Okay, we just saw that before. Okay, so let's talk about, so we talked about tension, no, weight, the easiest. Tension, very easy. Normal force, not that easy. So we talked about equilibrium. Now we're going to talk about frictional force. So you have two kinds of frictional force. You're going to have static frictional force when it's not moving, and then you have kinetic when it's moving. So, for example, if I want to move that desk, okay, so I push with one pound. Is it moving? It's gonna push back with 1 pound. That will be static friction. And then I push harder with 2 pounds. Is it moving? No. So that means static friction is 2 pounds. And then I keep pushing, pushing, and pushing until I reach the maximum static friction, and then it starts to move, and then I have kinetic friction. Okay, I think I already showed you that. Let's see. So here you have friction. I'm going to increase the friction. Okay, let's see if I skip here. Is it moving? Okay, so what's the net force? 0. Acceleration is 0. The static friction is 50. And I'm going to push harder, and the static friction is going to increase as well. So static friction increases until you reach a maximum. And then friction decreases, and then it becomes kinetic friction. Once it's kinetic friction, it's going to be constant. So let's keep pushing up, and now it's moving. So what type of friction do you have here? Kinetic. And let's see if it increases, if I push harder, or does it stay the same? Okay. Did you see it moving? Or does it stay the same, the kinetic friction? Oh, I see. It stays the same. So kinetic friction is always staying the same. Once you reach kinetic friction, it's not going to change. Okay, and the net force will be applied minus kinetic. Now you see what is the force now he let go? What's the force applied now? It's moving. So if you push something on the floor, it will eventually stop. Why is it stopping? Because it's acted upon by kinetic friction. Okay? And only kinetic friction. So you see you have kinetic friction, it didn't change. Okay? So the acceleration will be negative. So it's going to slow down, slow down, slow down, slow down, slow down. The acceleration is negative, and eventually it's going to stop. Agree? So for example, again, I'm going to push, nothing moves. Push, nothing move. Push. I'm going to try to find the maximum static friction. It's hard to find it. No. Yeah, look. Can you look? Because I cannot do two things at the same time. Try to find the maximum static friction just before it moves. No. Oh, okay. No, that's because I let go. So, okay, keep pushing. Keep pushing. 95, do you agree? I'm not there. 98, 100, 101. Does it move? No, 112. And 116, 117, 122. Ah, well, did you see the limit? One what? 120, 122, 125? Yeah. But what's the kinetic friction now? Do you see the kinetic friction on the left? 94. 94. So the static friction is going to increase, reaches a maximum, which was 122, and then it goes down at 94, and it will stay 94. Okay? So typical equation for the, I don't know, static friction is always largest larger than the kinetic friction. So how can you explain friction? Because when two materials are in contact, you see it's all molecules interacting with each other. You have hydrogen bond, whatever bonds, what I don't know exactly what's going on, but you see it's like hooked together. So you have to overcome this, right? And then it can start to slide. But even when it's sliding, you have friction. So when two surfaces are in contact, you have to deal with friction. Okay? So again, you pull and you're gonna have static friction pulling back. You pull harder, it's gonna pull harder. It's like a reaction force. And then once you reach a maximum, then you're gonna have kinetic friction. Is that clear? Right, everyone? I feel like people are spacing out, like doing something else on their computer. Can you focus like 5 minutes more? So you see the static friction is going to increase, 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 reach a maximum, and then it goes down. So what about the math? What are the math? The math are very easy. And it's going to be true only in magnitude. So we're going to have the maximum static friction. So that's going to be max equals 2. So it's in magnitude. The coefficient, which is called the static coefficient, times the normal force. Because it depends on how hard you are pushing on the ground. So harder you are pushing on the ground, more static friction you're going to get, which makes sense if you have something very, very heavy. It's pushing so much on the ground. You're going to have more hooking going on. Okay, the two surfaces will be hooked together. So, and that's the coefficient that will depend only on the material. So if you have rubber, for example, those special shoes that you want to use to climb, to do rock climbing, okay? So the coefficient will be very, very large, okay? Because you don't want to slide. If you want to do, obviously, ice skating, the coefficient between the ice and the ice skate will be very small, maybe 0. Is that clear? So it's an equation only in magnitude. And then you have the same equation for kinetic friction. So kinetic friction will be the coefficient times the normal force. And by the way, you know that you are supposed to read your textbook, right? You have solved problem, you have to read the chapters. Don't just rely on the lecture. That's not enough. You have to study from the book. Okay, so these are easy equations. So I want to show you some example. So for example, rubber on concrete, you're going to have a very large static friction and of course a large kinetic friction coefficient. The coefficients will be very large. If you have a Teflon on Teflon, that's going to be small. Copper on steel, that's going to be small. Right? Rubber on asphalt, it's going to be large. But if the asphalt is wet, it's going to be smaller. So that coefficient here, the coefficients have no unit. Agree? So the friction depends on the two materials in contact. So you can apply that if you try to climb, for example, you need those expensive shoes. It's like Bare Feet, I think it's a brand, and it's made of a special rubber that will to make sure that the static friction, the coefficient of static friction will be very large. Okay, and when you are climbing, you want to make sure that your center of mass will be just above your feet, okay, to increase the normal force. And if you increase the pressure, if you increase the normal force is like pressure, then you increase the static friction. Does it make sense? So it's called, do you know the brand? It's Barefoot or Bare Feet? Barefoot. barefoot, right? It's like $100 or something, but they are very good because they will stick very well, right?
Yeah.
So I used to live in New York, and in New York, it's great for hiking, which is not great here. Uh, and so there's a place in New York, north of New York City, which is called Cold Spring, and there was a special trail, and the trail is called Breakneck, and it's literally breaking neck, right? It's very hard. It's if you like hiking, if you like to climb rocks, like without ropes, anything, it's great to do. And just to give you an idea why static friction is important. So they had this petition in Indiana. That was before COVID. And you see the special shoes that they have? Okay, so they rely on static friction. You can even compute the coefficient of static friction. It's so cool. I wish I was there. Look at that. So it's a trail. You have to follow the trail, right? So this is the Hudson Valley. That's the Hudson River. If you follow the river, you're gonna go to New York City. And these people, I don't know what they are called, but they have so much energy. Look at that. Isn't that amazing? And it's raining. It's raining just before COVID. It's quite amazing. And they keep going. They keep going. Good. And now they're going down. So to go up, you have to climb all the rocks, right? Just above the Hudson River, you have a beautiful view, and then you have to go down.
Try to look sexy.
And you have to run and run and run.
The climbs in the second half, I wasn't sure.
And this is the winner.
Thank you. Pretty good.
But that's crazy, okay? It's 4 hours. 4 hours! 4 hours, but it's still crazy. It will take me 8 hours to do that, right? If I can make it to the top. So very important for rock climbing.